Okay, welcome back. We now have James Reed talking on functional freedom and Penrose critique of string theory.
Great. Yeah, thank you, everyone. Thanks for the organisers for putting it together, sorting this room out at short notice, etc. This, as you can see, is joint work with local hero Mate Kratky. And I think more of Mate's work will come out tomorrow. I guess he doesn't need to be here, he knows. So this paper actually came out about a year ago in the Philosophy of Physics journal, but there was a recent uptick of interest again in light of the fact that Sabine Vossenfelder covered it this year. So one of the things that she did is mock us for the number of footnotes. I don't think it's that bad, but you can tell it's written by us. Favorite words like fiber bundles, Enrique Gomes. Yeah. So she also I was a bit worried how she was going to rate it, but she gives it low on the BS scale. So hopefully I'll live up to that today. Okay, so here's the background. So in his popular books, The Road to Reality and Fashion, Faith and Fantasy, Penrose criticizes string theory and its practitioners on a number of grounds and from a number of different angles. I remember when I was a teenager reading Road to Reality and thinking, oh, yeah, man, he really doesn't like string theory. If only I could understand what he was saying. 20 years later, hopefully, I've managed to get my head around it. So today, I'll assess Penrose's conceptual and technical objections to string theory, focusing in particular on those which invoke a notion which he calls functional freedom. The plan is the following. So I'll tell you what Penrose means by functional freedom. We'll see how Penrose thinks that functional freedom has something to do with the equivalence or otherwise physical theories. I'll then give you relevant background on string theory and string fields theory. I'm sure everyone here has seen the basics of string theory, which I'm going to present before, but maybe you haven't seen string field theory, so I'll go over what I need to say there. And then we'll look at the four main arguments which Penrose gives against string theory and see if any of them are successful. And just as a spoiler, we think that these three are not successful, and more needs to be said about this last one. Cool. Okay, so here's functional freedom. So typically, when we're constructing a field theory, you begin with a manifold, which we can think of as a background on which physical events unfold. And these physical events pertain to fields which assign values to each point in the manifold. Of course, this is a bit more delicate in quantum field theory, but I will elide that. If you label those fields by phi's, you can think of them as functions which map from the manifold to this fi, where this fi is itself a differentiable manifold of field values. We can then introduce some standard philosophy jargon of kinematically and dynamically possible models. So you could say that the kinematically possible models of a given field theory are specified by these tuples of the manifold and then a bunch of fields on it. And the dynamically possible models are a subset of the kinematically possible models picked out by appropriate dynamics. So you might be interested in the dynamically possible models of Maxwell theory, electromagnetism, say, and those will be those kinematically possible models where these fields satisfy Maxwell's equations. And a field theory thus consists of a specification of the kinematically possible models together with some dynamics, which allow you to pick out the dynamically possible models from the kinematically possible models. Okay, so the next thing to say is about cardinality. So in The Road to Reality, Penrose provides plausibility arguments to the effect that the cardinality of the set of kinematically possible models will be AF1, regardless of the precise dimension of M or these differentiable manifold of field values, these FIs. That seems correct. And given that, therefore, for most of the field theories that we're looking at, the cardinality is the same for all cases, how are you to quantify and compare the degrees of freedom of one particular field theory versus another one? Penrose would like to do this, and so he wants to introduce some machinery which somehow cuts finer than cardinals. And he's going to introduce the notion of functional freedom. The way that he gets there is, first of all, by a discretization heuristic. So he proceeds by approximating the manifold and this manifold of field values by discrete manifolds consisting of only a finite or countable number of points. Or actually, let's say finite. And then one might try to recover the original manifolds from this picture by taking the limit as the number and density of points goes to infinity. So for example, consider the field value, which we'll call T, whose kinematically possible models are given by this differentiable manifold R3, where V is a three-dimensional vector field on R3. Now consider some discrete analog of this. Consider a three-dimensional cubic lattice of n cubed points, which is our replacement for R3, on which there lives a discretized three-vector field, formally V. In other words, suppose that each of these n cubed points is assigned a vector whose components can take one of k values. Just simple combinatorics tells you that the overall number of degrees of freedom here is k to the 3n cubed. As the total number of possible field configurations on the lattice, since each of the n cubed points is assigned one of their k cubed possible values. So for this finite theory, this would be the number of degrees of freedom. Generalizing, you could say that for a field with c independent components over a d-dimensional lattice, you would have this number of degrees of freedom, k to the c, n to the d, where d is the number of space-time dimensions. Of course, this guy's going to become infinite when you take the continuum limit, and the analysis will continue to will break down. But Penrose wants to continue to use it, and he does this by just putting the infinities in and carrying on using this to compare one field theory versus another one in terms of objects like this. So in trying to retain a sense of magnitude elusively captured by the above analysis, Penrose uses expressions like this to denote the functional freedom of your theory. Okay, I'm not saying this is something that we should do, but this is what Penrose does. Okay, so now that's just kinematics. Also think about dynamics. So suppose our theory has some non-trivial dynamics. Intuitively, your dynamical equation should cut down the functional freedom of your theory because it's specifying relations between the objects which are not hitherto specified. So to capture that fact, and now this is our terminology, you might distinguish the kinematical functional freedom of the theory obtained by ignoring its dynamics versus the dynamical functional freedom, which takes the dynamics into account. And the dynamical functional freedom, insofar as this notion makes sense, would be less than the kinematical functional freedom. As an example here, kinematically possible models of vacuum electromagnetism are given by these triples of manifold and a Minkowski metric on it, and a two-form, the Faraday tensor. For the purposes of obtaining dynamical functional freedom, following Penrose actually uses this example. It's convenient to represent the theory in terms of its three-component electric and magnetic fields. And then you can say the kinematical functional freedom of the theory is infinity to the 6, infinity to the 4, because you've got to populate a four-dimensional space-time, hence the 4 here, with two three-component vector fields, hence the 6 here. Now dynamics are implemented by the Maxwell's equations, and these admit of an initial value problem. So if you consider a three-dimensional spatial hypersurface, sigma, once you specify the E and B fields on sigma, you can use the dynamical Maxwell's equations to specify the fields off sigma. And that would seem to decrease the functional freedom from the original kinematical functional freedom of the theory, this guy, to this smaller number, because now I just need to specify my 6 degrees of freedom on the 3 surface. So instead of infinity to the 4 here, I've got infinity to the 3. But you have to exercise further care because actually I've still got other two Maxwell's equations which impose constraints, and that's going to further decrease the functional freedom of the theory. And in the end, you can arrive with Penrose at the verdict that the functional freedom of standard source-free electromagnetism is infinity to the 4, infinity to the cubed, once they take into account the constraints from the other two Maxwell's equations. There are some worries here that you might have. How do I incorporate gauge degrees of freedom into this framework? Should they be taken to contribute to the dynamical functional freedom of the theory, or should they be removed via gauge fixing? How about non-physical fields like ghosts in QFT, etc.? Penrose doesn't say a great deal about this. Mate and I try to flesh this out a bit. We talk about applying constraint analysis, famous constraint analysis from Henham and Teitelbaum to this kind of problem. But I won't need to say anything more about this today. I'm just flagging that this is something you might be worried about. Okay, so I mean, upshot so far, Penrose has introduced these kind of strange looking objects of infinity to the power of infinity with extra stuff around to try and quantify the extent to which one field theory has more functional freedom than another field theory. And he insists that this functional freedom does capture a sense of magnitude, but resists its identification with Cantor's theory of infinite cardinals. He writes in Faith, Fashion, and Fantasy The first point I should make is that these infinite numbers do not refer to the ordinary Cantor sense of cardinality that describes the sizes of general infinite sets. Cantor's theory of cardinal infinities is really concerned just with sets, which are not thought of as being structured as some kind of continuous space. For our purposes here, we do need to take into account continuity or smoothness aspects of the spaces that we're concerned with. For example, points of the one-dimensional line are just as numerous in Cantor's sense as points of the two-dimensional plane. However, when we think of these points of the real line or of the real plane, respectively, as organized into a continuous line or a continuous plane, the latter must indeed be thought of as a much larger entity in the limit when the finite n element set R becomes continuous. And that's not really obvious as an argument here. He's just saying, I actually think this is bigger than this. So some initial worries are that if Penrose maintains that functional freedom is not a cardinal number, yet believes that two functional freedoms can be meaningfully compared in size, it's tempting to accuse him of inconsistency, because the standard linguistic practice in mathematics uses the word larger, smaller, more, less, in terms of, at least when we're dealing with infinite things, Cantor's cardinals, or measure theory, or something like that. Engaging with this linguistic practice by making comparisons of functional freedom would therefore seem to commit Penrose to just functional freedom just being Cantor's cardinals, which is what he denies. It's tempting here, and again, this is something which we explore more in the paper, which I won't say more about today, to read Penrose is engaged in some kind of exercise of conceptual engineering, where he wants to update our knowledge of relative magnitudes, but we don't actually think that this goes through. But there's a whole book about conceptual engineering, which is relevant here. Okay, so far I've presented to you functional freedom in Penrose's mind and presented to you some prima facie worries about the notion. Let's try and give him the benefit of the doubt for the time being. Now, Penrose wants to use functional freedom as a criterion of equivalence of physical theories. He maintains that a theory cannot be equivalent to another theory on which the initial space has a different number d of dimensions, since the freedom in the d space always vastly exceeds that in the other theory. We read Penrose as proposing this necessary condition on the equivalence of theories, what we call EC. Theories T1 and T2 are equivalent only if they match with respect to their dynamical functional freedom. But you can cash this out or disambiguate it in a few different ways. So one would be to insist that two theories are physically equivalent. They describe exactly the same physical goings on, only if their dynamical functional freedom is the same. It would be sufficient to refute this to observe that a mismatch in dynamical functional freedom doesn't necessarily imply that they're physically inequivalent. And you might point to examples like, if you have quite a naive reading of gauge theories where you're not counting the gauge degrees of freedom, then you might say something like Faraday tensor electromagnetism has a different number of different amount of functional freedom to vector potential electromagnetism. You may or may not be convinced by that, depending upon how you take into account gauge degrees of freedom in this analysis, but that would be like a way of pumping your intuition so this might not be true. In the end, exactly what constitutes physical equivalence in the philosophical literature is itself a knotty business, and so it's hard to give clear adjudications on whether this is something that you want to buy into, absent like filling in the slot of exactly what you mean by physical equivalence. You could also, and actually this in the end is probably closer to what Penrose has in mind, try to understand this equivalence criterion in terms of empirical equivalence of two theories. So there's this standard distinction in the philosophy of science literature between two theories being weakly empirically equivalent, whereby they agree on all of the empirical data that we've gathered so far, but they might disagree when we do more experiments in the future, versus strongly empirically equivalent theories, which are always going to make exactly the same empirical predictions, and you'll never be able to distinguish which one is correct, insofar as you want to say that one is correct and the other's not. So you could disambiguate this equivalence criterion that Penrose proposes by either saying that theories T1 and T2 are weakly empirically equivalent only if they match on their dynamical functional freedom, or you could say theories T1 and T2 are strongly empirically equivalent only if they match on their dynamical functional freedom. This second equivalence criterion is plainly false. Like you can think about just like Newtonian gravity at some point is, or in some sense, in some regimes is weakly empirically equivalent with general relativity, but they have different amounts of dynamical functional freedom. The second one, this EC3 seems contentious. Why should strong empirical equivalence require the same amount of dynamical or functional freedom? You might point to literal interpretations of gauge theories, for example, to make you worry about this. Actually, we think that the case that EC3 isn't always going to be something that you want to buy into. It can be made clearer by looking at some quantum theories, which I'll tell you about in just a second. So what if we now allow our theories to be quantum theories? So far, my presentation was kind of classical. One naive thing that you might say is, pending a counting algorithm for quantum theories, you could say that we're going to adopt this prescription according to which the dynamical functional freedom of some quantum theory is just the dynamical functional freedom of the classical theory of which it is a quantization. It's kind of dicey, but let's roll with this. Then EC2 would remain highly implausible, but new problems cases for EC3 would emerge. So to give one example of this, what's known as the world line approach to quantum field theory seems like a blatant violation of EC3. In this theory, scattering amplitudes aren't calculated from space-time fields, but rather from world lines by performing path integrals of world line models. And the scattering amplitudes obtained from the world line methods agree with the ones obtained by the second quantization of fields, your quantum field theory on space-time, despite the fact that the functional freedoms of the two theories differ significantly. So I've got two strongly empirically equivalent theories, but it really does seem like their dynamical functional freedom is different, which might make you unhappy with EC3 as well. So just to summarize that, if you buy into EC1 about necessary condition for the physical equivalence of theories being that they coincide with respect to their dynamical functional freedom, you need to say more about what physical equivalence means. When it comes to EC2 about weak empirical equivalence, that just seems wrong. And EC3, I think there's good examples which might make you worry about it. Okay, so now let's move on to string theory. I'll tell you a little bit about what we need to say about string theory for our purposes of discussing the Penrose's criticisms of it, and then we'll bring these things together when we look at Penrose's arguments against string theory. So, yeah, I guess everyone knows this, right? How many people know this? Oh, okay, well, whatever. People always talk about Jeremy Butterfield, but I think we've overdone that. So, okay, classically, a relativistic string in Minkowski spacetime is described by the Nambu-Goto action, which describes how this string oscillates in the ambient spacetime. And this sigma is the string world sheet, and these functions x describe the embedding of the world sheet into Minkowski spacetime. This is a Poincare invariant action and also invariant under world sheet reparameterizations. It's difficult to quantize the Nambu-Goto action due to the square roots there. So what string theorists typically do is resort to the classically equivalent Polyakov action, which is this guy, where we've introduced this auxiliary world sheet metric on the string world sheet, which can be removed via its equation of motion to get you back to the Nambu-Goto action. And on top of reparameterization and Poincare invariance, this is also invariant under Weyl rescalings like conformal space-time or world sheet position dependent rescalings of the world sheet metric, which is going to be of importance when quantizing the theory. There are lots of different ways that you can quantize the Polyakov action. I seem to remember this taking about 20 hours of my life when I did it in grad school. But one way that you could do it is view the Polyakov action as describing a 2D conformal field theory on the world sheet and perform a path integral over the world sheet fields, including these x's as well as the world sheet metric and a set of ghost fields, which are necessary mathematical tricks required by the reparameterization invariance of the theory. Suffice it to say, we don't need to go into the details of how we quantize the string. Once I have a quantized string, I can study its excited states, and famously, first excited states of a closed string will include something which looks like a graviton, which is why people thought that this had something to do with quantum gravity. And then I want to move from those excited states of the string to new background fields on space-time and ultimately leverage something like this way of thinking to derive something like the Einstein equations or generalizations thereof on the background ambient space-time in which the string is oscillating. And the prescription, to be very brief, is something like this. You quantize the string, you define ladder operators, raising and lowering operators, you study the excited states of the string, you move from these excited states to coherent string states on the manifold. This is a a philosophical step, which people like Nick Huggett have, I think, rightly said is quite fast in string theory textbooks, which we might want to say more about. How is it that we get from the excited state of one string to like a classical string, a classical field on the background space-time, which has the same kind of properties as it. But let's just assume this can be done. I guess the idea is you have a whole field of strings and then you kind of zoom out and ignore the stringy effects and ignore the quantum effects. And then use, importantly, world sheet invariance to argue that the background fields, which I've introduced from this step, in fact, have to be dynamical and have to obey generalizations of the Einstein field equations. So once I, via this step, introduce these extra background fields on space-time, I then look at the world sheet invariance of the theory to derive constraints on what those background fields have to do. Yeah, and philosophers have looked at all of this procedure. The moral so far would be that perturbative string theory can be viewed as a 2D conformal field theory, which upon path integral quantization yields consistency conditions on the backgrounds in which the string propagates. If we're writing things in a field theoretic type framework, you might say that the kinematically possible models of perturbative string theory are picked out by this world sheet, and then these X's, these fields on the world sheet, and these CIs, which are the ghost fields that I had to introduce on it as well. But there is, however, an alternative view on string theory, according to which string theory is itself a field theory. So this is something that's like the second quantized version of string theory, and this is known as string field theory, which has been rumbling around for several decades, but there's been a bit of an uptick in interest recently. This book on it from Urban came out in 2021. Banu will say vastly more about string field theory tomorrow. But here's the background for what we need to know today. So the fundamental objects of string field theory are open or closed string fields which live on the space-time M. So you could say that the kinematically possible models of a string field theory would be picked out by M, and then these closed and open and closed string fields on M. But that simple form would belie a lot of structure going on here. In perturbative string theory, excitations of the string give rise to a tachyon, a massless gauge boson, and infinitely more massive particles of higher spin when I study higher and higher excited states. And all of this is packed into the string field. So you can write states of the string field like this, and then you can actually expand this guy out, and what you end up seeing the string field encodes is kind of infinitely many quantum fields associated with all of the different excited states of the string. And it's thinking about those like at every point in space-time. So there's really quite a lot going on, and hence it's no surprise it's quite a difficult thing to work on. I'm going to refer back to string field theory when I talk about some of these criticisms from Penrose. Is everyone okay so far? Good. Okay. All right, so now let's go through Penrose's arguments against string theory, which rely on his notion of functional freedom. So his first argument has to do with counting functional freedom. And actually, there are three kind of sub-arguments here, three functional freedom counting sub-arguments against string theory, which you can find scattered across his writings. And we'll call these the classical physics argument and the heterotic string argument and the ADS CFT argument. So let's go through them each in turn. So the classical physics argument, which you can find in Faith, Fashion, and Fantasy, observes that the discrepancy in the dynamical functional freedom between world sheet perturbative string theory on the one hand and what Penrose calls ordinary physics on the other, which is not really specified, but I take him to mean kind of the physics that we currently have, like general relativity and things that we have better control over. There's going to be a big discrepancy here. Infinity A to the infinity 1 over here versus infinity B to cubed over here, and concludes that this is somehow problematic, that there's this discrepancy in dynamical functional freedom of perturbative string theory versus ordinary physics. And in addition, he observes that the full functional freedom of world sheet string theory might not be easily ascertainable from the formulation of the theory. Those are actually worries of a different character, even though they're kind of right next to each other in Penrose's writings. This is an epistemological issue that you might not be able to figure out easily what the functional freedom of perturbative string theory is. Whereas this is more, there's some kind of inherent problem with it because it disagrees with the functional freedom of classical physics, so more metaphysical in nature. On the epistemic worry, we don't see why this should actually count as an objection. It seems to be more a limitation of the theorist rather than of the theory. Why should the fact that you can't easily ascertain a number of degrees of freedom make the theory itself problematic? On the metaphysical worry, we don't see why either perturbative string theory or string field theory should be obliged to reproduce the functional freedom of ordinary physics. Presumably, it's only the case that perturbative string theory or string field theory is weakly empirically equivalent to ordinary physics in the appropriate regime, whatever that means. But we've already rejected the equivalence criterion on which that seems to be relying, namely equivalence criterion 2. And so this argument doesn't seem to go through. So let's move on to the second argument, which is actually just, I think, a worry that he doesn't get what's going on with the heterotic string. I'll read out the quote. So the heterotic string is one of the 5 string theories. The strange feature, he says, about heterotic string theory is that it appears to behave simultaneously as a theory in 26 space-time dimensions and in 10 space-time dimensions, the latter with accompanying supersymmetry, depending upon whether we are concerned with left-moving or right-moving excitations of the string. So that's a true summary of what's going on with the heterotic string. This dimensional conflict would seem to cause us problems if we're to try to work out the functional freedom involved. I find it very difficult to form a consistent picture of what's going on here, and I've never even seen these geometrical issues properly discussed. I agree it's kind of strange. However, when one looks at the physics literature on the heterotic string, there seems to be a pretty broad, in fact, basically universal consensus that the dimension in which these strings are situated is 10. This is just a quote from Erdős' book on string field theory. And so it seems we can actually fill in like that top number in the functional freedom of the theory that's to do with the number of space-time dimensions. So it's not obvious that there is the kind of confusing issue that Penrose seems to think there are when it comes to the heterotic string. It seems like string theorists would be able to give a determinate answer to him, at least conditional on the notion of functional freedom making sense. So the heterotic string field theory, this is what Ervin's talking about here, seems to be formulated unproblematically on d-dimensional spacetime, d equals 10. Would this be a consistent geometrical picture for Penrose? In any case, of course, we're skeptical about the relevance of functional freedom to these considerations. All right, and the third functional freedom counting argument is what Penrose calls the ADS-CFT argument. So Penrose sees a problem in the mismatch in dimensionality and hence functional freedom, again, when I'm thinking about that top number, between the ADS side of the ADS-CFT correspondence and the CFT side, and takes this to indicate that these theories cannot in fact be equivalent empirically or otherwise, based upon his equivalence criteria that we saw before. There's lots to say here. First of all, it's an open question whether these theories have the same dynamical functional freedom or not when you properly take into account like how the duality is working. And if they do, then Penrose's arguments would be moot. But in any case, why should a mismatch in functional freedom imply empirical equivalence, either weak empirical equivalence or or why can't I have theories which have a mismatch in their dynamical functional freedom and yet be strongly empirically equivalent as well? These are questions that you can ask, which seem fine situations to us, but which Penrose evidently doesn't like on the basis of his equivalence criteria. Okay, so arguments to do with counting functional freedom don't seem obvious to work when one looks into them a little bit. The next kind of argument that Penrose gives is an argument to do with exciting extra degrees of freedom in string theory. He worries that the theory cannot be empirically adequate when one thinks about how the extra functional freedom or degrees of freedom associated with the extra functional freedom of string theory can be excited. To talk about this, we first of all have to say a little bit about compactification. So in order to recover 4D phenomenology in string theory, theorists have studied models in which the additional dimensions, 22 for the bosonic string or 6 for the superstring, are compactified onto a manifold of small size. Typically, in the superstring, those are taken to be Calabi-Yau threefolds, so that the string theoretic spacetime in the end takes this product form of M cross X, where X is this Calabi-Yau. The number of possible Calabi-Yau compactifications is very big, and this leads to, in the literature, what's known as the landscape problem of possible string theory compactifications, about which Selvin reference. Batiste and I wrote a paper a few years ago. Here's how compactification works in brief, in a simple example. So first of all, consider the product manifold M cross S, where M is our familiar four-dimensional Minkowski space-time, S is a small circle. So this is something like what's known as Kaluza-Klein compactification. The Klein-Gordon equation on that manifold could take this form, where this theta denotes the coordinates along the compactified dimension, and this is the usual D'Alembert on M. You can separate out the modes for the field associated with this dimension by writing the field like this. And in that case, the Klein-Gordon equation takes this particular form. And then you can notice that as the radius becomes small, the masses become big and hence undetectable. That's the kind of reasoning which is going on here. So as I make my compactified dimensions super small, I shouldn't be able to see them. And something like that kind of methodology for compactification is going on in string theory as well, albeit more complicated because we're dealing with the Calabi-Yaus. So Penrose now thinks about what it would take to excite NB. It's not clear what excite means here, but let's carry on. These extra degrees of freedom, these extra dimensions, which we have in string theory. Here's him talking about this in The Road to Reality. Are the positive energy Planck scale modes of vibration of the 6 extra dimensions immune from excitation? Although the Planck energy is indeed very large when compared with the normal particle physics energies, it's still not that big an energy, being comparable with the energy released in the explosion of about 1 ton of TNT. There is, of course, enormously more energy than this available in the known universe. For example, the energy received from the sun by the Earth in 1 second is some 10 to the 8 times larger. On energy terms alone, this would be far more than sufficient to excite the compact space for the entire universe. Yeah, I'm seeing some puzzled faces. I'm puzzled as well. I kind of forgive my teenage self for not understanding it. Okay, so let's assess this argument. So crucial in this passage seems to be the notion of exciting a degree of freedom. What this actually means is unclear. Perhaps one way that you might hash this out would be to appeal to string field theory. So I have string fields on space-time, and their various components can be excited just as with ordinary quantum fields. But this doesn't seem to square completely. If excitations of the string field around the background coherent state were to occur, that would surely need to be facilitated by local means rather than TNT explosions, something which Penrose rejects. He rejects that I need to localize the energy in order to excite the field. In standard QFT, it's localized energy which is relevant, and why should the situation be any different in string theory? Also, when Penrose says the entire universe can be excited, I don't know what he means. So it would seem to presuppose that all copies of this compactified dimension are distributed over the manifold will get excited in the same way. But like, how does that actually follow? My manifold had this product form, and you would think that any excitation of these spaces would have happen locally in the manifold. It wouldn't be like you do something over here and it excites stuff over there. So at any particular point in the manifold, one excites the X space, but this doesn't automatically translate into excitations of X far away in the Andromeda galaxy. So a puzzling argument. Okay, the third one, classical instability of extra degrees of freedom. This argument relies on singularity theorems, which famously Penrose, along with Hawking, proved in the 1960s through early 1970s. And the assumption behind Penrose's reasoning here seems to be that the background fields in string theory are to an excellent approximation described by the Einstein field equations of general relativity, derived in this way via the world sheet analysis constraining the background fields, which I talked about before, which here I've telegraphically called the beta function analysis. But note that this is only an approximation to the full dynamics. Actually, I don't just have the Einstein field equations on the target space. I have Einstein field equations plus corrections, and we'll come back to that. Now, the singularity theorem, which Penrose invokes, works as follows. So first of all, consider a compactified string theoretic space-time as before, where X is again a small Calabi-Yau, and let's let M be the background space-time. Since M has this product form, let's assume that it's globally hyperbolic, we can regroup the terms and then define the Z as R cross X. And then we can impose perturbations on an initial value surface in Z and study the propagation of these perturbations into the future. And then we can wheel out these singularity theorems. So this theorem from 1970 of Hawking and Penrose says that this evolution will result in a singularity, provided that the dimension of Z is greater than 3 and Z contains a compact n-1 dimensional hypersurface without closed time-like curves. And the Einstein tensor satisfies the strong energy condition, which is this guy. And on this, Penrose says, what this singularity theorem appears to be telling us is that so long as the perturbations of the extra dimensions can be treated classically, as indeed appears to be a reasonable thing to do as a clear conclusion of our earlier considerations, then we must expect a violent instability in the 6 extra spatial dimensions in which they crumple up and approach a singular state. Whatever the extra dimensions might crumple to, the observed physics is not likely to be other than drastically affected. This is hardly a comfortable picture of the 10-dimensional spacetime that string theorists have been proposing for our universe. So Penrose seems to think that the strong energy condition is certainly satisfied in string theory because it follows from the vacuum Einstein equations, which Penrose assumes to hold on the spacetime that we're considering here. But let's remember that the full dynamics of the background fields in string theory, as I said, are not just the Einstein field equations, but rather plus infinitely many correction terms. And the Einstein field equations are only a low energy approximation to the full equations which you get. So an appeal to the Einstein equations in justifying this condition isn't completely watertight. And even granting the Penrose the low order approximation of the full dynamic, the vacuum Einstein equations are certainly not an accurate model for string theoretic backgrounds because I get like material dynamics out of this analysis as well. If you want to actually use an energy condition more native to string theory, you could appeal to some recent work. So in 2015, people derived the geometric null energy condition in perturbative string theory, but this doesn't imply the strong energy condition. So it's not clear that this helps Penrose out. Penrose would have to use a different singularity theorem if he wanted to illustrate his point. Okay, and here's the fourth argument about initial data. The last, I think, long quote from Penrose. He says, more serious to my mind is the fact that the full requirement involving all orders in the string constant alpha is actually an infinite system of differential equations of unbounded differential order. Accordingly, data that would be needed on an initial 9 surface would involve derivatives of all orders in the field quantities, rather than just 3, the first or second derivatives. I'm a bit worried. There's a lot of typos in here, and I copied it from the published paper. So anyway, I needed for ordinary theories. The number of parameters per point needed on the 9 surface is then infinite, so we get a functional freedom greater than this guy for any positive integer m. This would seem to make the problem of excessive functional freedom even worse than before. I'm not aware of any serious discussion of the mathematical form of this full requirement and of what kind of requirement on initial data might be appropriate for it. So response, we don't regard the infinity of terms and their unbounded differential order as inherently problematic for string theory, because in principle, the Cauchy problem could still be well-defined and the system solution still existent and well-behaved. But that's as long as convergence to actually arrive at these equations is actually secured. Beta functions which you use to get the target space fields, the fields on space-time, don't in general converge, which seems to make this problem a bit more pressing. So this is the case where we think that, Penrose's argument is not obviously wrong. More work needs to be done on this one. Okay, let me wrap up. So Penrose raises many arguments against string theory, relying on the notion of functional freedom. I've questioned whether the notion of functional freedom is well-defined or coherent. I've also discussed the relevance of functional freedom for notions of theoretical equivalence, and it's less obvious than Penrose suggested it is when you disambiguate what notion of equivalence you have in mind. And in any case, most but not all of Penrose's arguments against string theory seem unsuccessful when you dig into them. So thanks. We have defended the orthodoxy.
Thank you very much. We have 20 minutes for Q&A, so please raise your hands. Yes.
Thank you. That was very interesting. I was wondering why he doesn't base equivalence just on This is equivalence of phase space variables rather than this functional freedom. That to me sounds more equal, and you don't have to deal with all these infinities.
Yeah, I think that's a good question. I mean, in physics and in philosophy, there are many ways that you might want to. People have elaborated on what it means for theories to be equivalent, and he doesn't talk about any of them. And I agree that this would be one thing that he could talk about. He simply says that a necessary condition for equivalence of theories is that they share dynamical functional freedom. Yeah, and given all of the other options on the table, it's not obvious that this is the thing to go to, really. So I think I'm simply agreeing with you.
Yeah, thank you, James. Just on the last point about the Cauchy problem,
Yeah.
like I agree that that is in principle still open. I'm rather confused as to why that has anything to do with the functional freedom stuff.
Yeah, good question.
Like,
sorry, I should have been maybe a little bit clearer about this. So the thing which is also slightly difficult. I mean, I don't want to sound like I'm beating up on these books because I actually think they're both great, but something which is difficult for someone that's trying to tease things apart as a philosopher is that actually all of these objections kind of run together. And so Mate and I made an effort to tease out the different threads of Penrose's argumentation. And I agree that this doesn't really have anything to do with functional freedom. It's just a worry that you don't have like a well post Cauchy problem, which may or may not be true.
Yeah. But then I don't understand. Yeah, I don't know. I find this whole functional freedom business quite confusing at this point. Like, what's the point of even introducing this notion?
Well,
because it seems obviously false in 90% of the like the ADS-CFT1. I think is kind of like another damning example that it's not doing what he wants it to do.
Yeah, I completely agree. But I think Penrose is a big name who's making novel arguments against string theory, and at least the burden is on us to try and take them seriously. And from my point of view, Mate and I did a pretty effective takedown, but saying both the notion doesn't make much sense, and even if it did make sense, the application to string theory is specious. But one has to do the hard work of like trying to be charitable.
Thank you very much. So I agree that this idea of functional freedom is very interesting, but ill-defined, and it's sort of not obvious why we should take it seriously. But if we try to do that, as you have done, as a notion of theoretical equivalence or something like that, at some point in that second part where you discuss this, you sort of moved from physical equivalence to empirical equivalence.
Yeah.
And it seems quite obvious to me that the empirical equivalence is way too coarse-grained a notion of equivalence, that this could possibly be what one has in mind when you do that. And I think it's pretty straightforward to find counterexamples, as you said. So presumably it would have to be some sort of finer grained notion of theoretical equivalence. So have you thought about that? Do you have any?
I think when you look at Penrose's writing, I don't think these are the best way of cashing out the connection, if there is any, between functional freedom and equivalence. But I think these are actually the ones that are like the ones he has in mind, and even the weak empirical equivalence one, which is surprising, right?
Okay. But suppose now, I mean, this may well be the case that Penrose has this in mind, but if we agree that this is not going to run very far, let's try to make sense of this prima facie interesting idea of functional freedom. Could it function as a notion of theoretical equivalence which is more fine-grained? Sort of not just reducing the theoretical content to its empirical implications, but some sort of more metaphysically beefy notion of theoretical equivalence.
I'll say something and you can tell me if it answers your question. So I think Mate and I are of the view that this is the best one going, but it's going to depend upon your understanding of how you deal with gauge degrees of freedom in infinite theory.
Of course.
So if I'm like quotienting out gauge degrees of freedom in vector potential electromagnetism, then I am actually going to have the same dynamical functional freedom as Faraday tensor electromagnetism. And so that's when I'm treating gauge degrees of freedom in a certain way, namely by excising them and assuming that I have a prescription to do that, then it might be that this is a plausible necessary condition on physical equivalence.
Yeah.
I'm not sure if that's what you had in mind with fine grace.
Something in that, yes, in that direction, absolutely.
And so we're like, in the paper, we say, basically what I just said, this is the best one going, but you need to flesh out the details, flesh out how you're dealing with these other issues.
That'd be an interesting project.
Yeah, I agree. Yeah. Maybe one other thing to say, I don't really know this literature at all, but apparently in the philosophy of religion, for reasons that aren't clear to me, people have tried to introduce ways of cutting finer than Cantor's cardinals. I haven't connected up our paper with that stuff, but it might be something to look into.
I mean, do you have a sense if moving to physical equivalence would change anything for those arguments about string theory? Because at least on its face, it doesn't seem like it would improve.
I don't think so. And when you look at the arguments like the ADS-CFT argument, or
that
the
really requires,
it's like clear that he has empirical equivalence in mind. So the charitable patching up of Penrose on this front would obviate some of his criticisms later.
Yeah.
Yes, just a remark about the last part. I also, in the book, I was always fairly confused why he considered weak empirical equivalence important at all. Yeah. Yes. With regard to the last point, to the initial state issue, does it seem to you that, it seemed to me that this is entirely within the framework of a perturbative understanding of the theory, so he doesn't seem to address the full theory.
That's true. Yeah, because he's thinking about the equations that you get from the world sheet beta function analysis. Right, is that what you have in mind?
In a way, he seems, I mean, he may have a point in pointing at that the perturbative approach on its own can't stand on its own. So maybe that's basically what he's pointing.
I think that's fair. Once we have some other approach on the table, maybe we can come back to whether his fourth criticism here is something that we want to buy into.
So my question was very close to what Chris asked, so I'll just ask like a clarificatory one, or at least if you could expand a bit on what is the expectancy on the argument on the CFT discussed by Penrose that dynamical functional freedom of the duals could potentially be the same. So why would you expect that, and how is that?
Yeah, let's go back to this argument. I think that the thing that's most straightforward to read Penrose as saying is that because of the mismatch in dimensionality, which corresponds to that bigger number in functional freedom, they don't have the same functional freedom. And so they should be empirically inequivalent. Hence, ADS-CFT is wrong. I don't think that's what you were just asking.
No, I was just asking because you wrote that there's an open question whether.
Yeah. Again, I think you need to take into kind of a more sophisticated understanding of the number of degrees of freedom on either side. You're not just counting the number of space-time dimensions, but you're taking into account like how the mapping works and what's the gauge degree of freedom on both sides, etc. And maybe they actually do have the same dynamical functional freedom once you do that. Comes back to these other questions about like cashing this out properly. And if you end up saying that they have the same dynamical functional freedom, then his point, which I don't think is a sensible one really anyway, wouldn't even get off the ground.
Sure.
Yeah, maybe just a small question, but so you picked it up all these arguments from his book. Were those arguments also picked up by string theorists?
No, that's a weird thing, at least not to my knowledge. And Matty and I did a lot of searching around, and I think it's I'd love to hear people's like sociological conjectures as to why string theorists didn't engage with Penrose's arguments. Is because they thought that they were silly, or
just because they don't want to question string theory in this place. I don't know. Yeah.
I don't know. I welcome anyone's views about this.
How do you feel about that?
Well, I mean, I would strongly think so. I mean, I back then I wrote this this review for science, and I was fairly convinced that they asked me because they didn't find a string theorist who wanted to write it.
Oh, right.
I mean, I don't know that at all, but I thought that was the explanation.
Sorry, which book did you review? Faith,
The-
Fashion, and Fantasy?
yes.
Okay, I didn't even.
Yes,
My
yes.
bad. I didn't realize
Yeah.
you. Did you talk about this in there?
Yeah, I mean, it's a long time ago.
Okay, I'm sorry. I didn't even know that you. I need to check your review.
So it seemed to me that that's the only explanation.
Uh-huh.
Why?
Or it might be just there's so much like kind of exciting physics to be working
Yeah.
on with duality
Yeah.
and so on. Why would you spend your time like?
I feel that they felt they did not want to have an overly harsh reaction to Penrose, but
Okay.
they thought that these arguments were nonsensical. But quite frankly,
Yeah, some problem. Yeah.
And what did Sabine said about your article then? Sabine also said.
She liked it.
She liked
She was
it.
like, it was like scientific dialogue done right.
Okay.
It's supposed to be a lot of fun about it.
And there's one last thing, maybe. On the singularity theorem
Yeah.
part, have you tried to look, because now that people try to prove these singularity theorems which don't rely on things like energy conditions, like they're supposed to hold beyond GR, at least in some like semi-classical gravity thing.
Like the wall thing.
Yeah, exactly. And then Busho is working on them now. Do you have any, have you tried to look at that, if it like makes any kind of difference to what he's saying there?
Like Wall talks about like the generalized second law and quantum
Yeah.
trap surfaces and stuff.
Yeah.
Like it's not super clear to me how you would like
Translate
couple that to this discussion. But make yeah. Something that is more apt to be applicable to quantum theories, I agree, would be something that would be more sensible to look
Yeah.
at. And I agree it's a good avenue for pursuit, but I'm just not exactly sure how to match them.
I'm a bit confused, so just so you help me to clarify a bit the relation between functional freedom and duality, and your approach to the way of thinking about the kinematical dynamical distinction in terms of the dynamical models being a subpart of the kinematical models. So if you think of the metaphysics of a degree of freedom, it's kind of a model notion, right? There is some kind of so it's kind of quantifying the number of entities and their freedom. But if you have a duality between two theories, right, relating to two spaces of solutions, so there is no kind of what's the link between the cardinality of the space of dynamical solutions and the functional freedom? How do they relate the two notions? Because I was just thinking, why isn't the case? So let me ask this: could you explain to me why it's not the case that if you have a duality between two theories, then the cardinalities of the two spaces of dynamical solutions are the same? So it should be the same functional freedom. So what's the bit I'm missing here?
Sometimes the duality only works like up to gauge, right? And so I have one model over here, but it might be like a plurality of gauge related models over here.
Mm-hmm.
And so you have to talk in terms of functional freedom rather than cardinality, because actually the cardinality of these two sets is the same, but the functional freedom of this guy over here, you might say, is still naively bigger than the functional freedom over here, because there's more solutions over here, which this whole orbit is related to this model over here. But it's going to depend on how you actually like articulate the functional freedom of this theory with gauge symmetries or whatever. Do I need to quotient out the gauge symmetries first? And then I agree that there would be a one-to-one mapping of functional freedoms.
Right.
Which is actually the sense in which Penrose's like first criterion, EC1, or what we were calling EC1, might be okay. Like once you actually treat all of the intricacies of this guy, in the end, there should be a one-to-one mapping. So coincidence of dynamical functional freedom should be a necessary condition on physical equivalent.
Good, thanks, Phil.
If we have no other question, then please join me in thanking again our speaker.